8.5 Acid deposition. Acid deposition, process by which acid-forming pollutants are deposited on the Earth's surface. Nice little diagram showing you that these pollutants come from both man-made sources and natural. Volcanoes down here as an example. Now, I mentioned before I continue on here, this topic is all qualitative. There's a few equations you need to know, but mostly it's just informational. Acid rain. Normal rainwater has a pH of 5.6 due to the carbon dioxide reacting with water in the atmosphere. And you've seen this before. Remember, non-metallic oxides react with water to form oxyacids, in this case, carbonic acid. Now, carbonic acid will ionize to form hydrogen ions, making it acidic, and the bicarbonate ions. Now, the bicarbonate ions also can ionize to form even more hydrogen ions. So because of this very natural process, all water in the atmosphere is slightly acidic, a pH of 5.6. Rainwater with a pH less than 5.6 is called acid rain. The most common sources of this acidity are the oxides of nitrogen and sulfur, which will be our main focus. So again, please understand, the carbon dioxide in the atmosphere does not make the atmosphere, or does not cause acid rain to form. Acid rain forms due to further pollutants, specifically oxides of nitrogen and sulfur. Now, that you're not responsible for this, but carbon dioxide often gets kind of a bad rap as like this really bad thing, but it's part of our natural world. And so over on the left and the middle here, you can kind of see the natural process. Plants, vegetation take in carbon dioxide and give off oxygen. It's very important for the world that we live in. It's dissolved in water and then evaporated back out. Over on the right side is where we get into trouble. When we burn fossil fuels, we have more carbon dioxide going into the atmosphere. Now, even though we have more carbon dioxide in the atmosphere and it is absolutely problematic, it does not cause any more acidity in the environment. There's a limit to how much acidity carbon dioxide can cause. The problem with carbon dioxide is that it is a greenhouse gas, which is a story for another day where we won't be hitting it, but it helps to trap in heat. And so because of the excess carbon dioxide in the atmosphere, we have this very, very real problem of global warming. However, as far as our topic at hand, acid deposition, it's not a factor. Atmospheric formations of acids. You're not responsible for this. I just thought I'd kind of show you the relationship. So this is carbon dioxide, and then we go down here, we start getting into problematic acidities. Nitrogen oxides, sulfur oxides. This is where things get problematic. So carbon dioxide, as far as the acidity in the environment, is a good thing. Beyond that, not so good. The major atmospheric pollutants are sulfur dioxide, nitrogen monoxide, and nitrogen dioxide. Natural sources of these compounds: volcanic eruptions, lightning, forest fires, decomposition of vegetation. So all of this has been around since the beginning of time. Then enters the human race: anthropogenic, human-caused sources. Smelting, which is the heating of ore to extract metals. Ore is valuable minerals, rocks that have embedded within them important minerals, important metals. And if you heat that up, you can remove those, and that process is called smelting. But mainly it's the combustion of fossil fuels. Fossil fuels, oil, gasoline, things like that. Nitrogen oxides. Although not a fuel, nitrogen makes up nearly 80% of the atmosphere and is present whenever a fuel is burned, such as in internal combustion engines of cars. At such high temperatures, nitrogen itself undergoes combustion. Now remember, nitrogen has a triple bond between its atoms, so it's really hard to break that bond. But at the very, very high temperatures of internal combustion engines, the burning of fossil fuels, we can have this reaction take place. We do have it take place. Now the nitrogen monoxide is a very, very reactive molecule. If you stop to think about it, how many valence electrons does it have total? It has 11. Nitrogen has 5, oxygen has 6. So an odd number of electrons is very, very reactive. Most molecules, stable molecules, have an even number of electrons so that all their orbitals are filled, either by individual electrons that the atoms have themselves or by sharing. But when you have an odd number, it's very reactive. So the nitrogen monoxide then reacts with atmospheric oxygen. Now, the nitrogen that reacted with oxygen that we just talked about, that's at very high temperature. So you really have to force that reaction to take place, such high temperatures. But the nitrogen monoxide doesn't need to be at high temperatures. It immediately just reacts with the atmospheric oxygen to form nitrogen dioxide. The nitrogen dioxide you're most familiar with, it's the brown color that you see on a smoggy day. We don't have that problem here in Portland too much, but if ever you've gone to a city that has air pollution problems, that brown haze that hovers over cities is due to nitrogen dioxide. I grew up in Los Angeles, so I'm very, very familiar with that, too familiar with that. Nitrogen dioxide then reacts with water to produce both nitric and nitrous acids. Nitric acid is a strong acid. Nitrous acid is a weak acid. So nitrous acid isn't very problematic. However, wouldn't you know, it is easily oxidized to become nitric acid. So nitrous acid reacting with oxygen to form nitric acid. So again, nitric acid is a strong acid, so that's problematic. The term oxidized, you'll be more familiar with that term next month when we get to our unit on oxidation reduction. Now let's look at sulfur oxides. Now you don't need to copy this down, but since our focus, as we'll see, is coal burning, you can see that coal burning is not really too large a percentage of the overall sources of energy in the United States. This is from 2019. So 37% from oil, gasoline, 32% natural gas, nuclear energy, 8%, renewable, solar, hydroelectric, wind, etc., about 11%, and that's growing. That's a really booming industry. But it's coal that we're going to be interested in, and that is in coal-burning plants that will produce sulfur oxides, as we'll see. Now, before we get to that, I thought you might be interested to see the energy sources in Oregon. This is from 2016. 56.7% comes from hydroelectric, from dams. Only 3.2% comes from burning coal, which is what we're about to discuss. Burning coal is much more common on the East Coast. Coal contains about 3% of sulfur. When burned, it produces sulfur dioxide, meaning that when we burn coal, only 3% of it is sulfur, but that 3% is problematic. The sulfur forms sulfur dioxide. Sulfur dioxide can then react with water to form sulfurous acid. Or it can be oxidized to form sulfur trioxide. Now this should look familiar to you. This is from our last unit. Remember, this is the first step in the contact process. This equation we use many times as an example for how temperature or pressure affects the shift of the reaction. It was the sulfur trioxide that we were focused on, but then a little while ago, I think last week, we talked about all we needed to do was add that to water to get sulfuric acid. So these last two steps you've seen before in the contact process. But the Sulfuric acid ultimately comes from the 3% of sulfur that's in coal. Some effects of acid rain. Deforestation. The leaching of dangerous metal ions from rock into soil water, such as the aluminum ion. So when you have an acid, whatever that acid might be, an acid of sulfur or nitrogen, it can react with aluminum oxide. Now, aluminum oxide is better known as bauxite. Bauxite is a rock, it's a mineral that's found in rocks. It's very, very common. And when the acid reacts with bauxite, it removes aluminum ions. So the acid, remember, acids are always aqueous, so acid rain will form aluminum ions that are in solution, and that's very, very poisonous to trees. Decay of statues and building materials. This is the Roman Colosseum. Limestone and marble are common building materials, both containing calcium carbonate, which will react with acids. So the acid, whatever that acid might be, reacts with calcium carbonate to form carbon dioxide. Remember, an acid and a carbonate forms carbon dioxide, water, and a salt. Now we're leaving the anion of the acid off because it could be any of the acids we've talked about. So that anion is off here. But let's say it was sulfuric acid. Well, then this would be calcium sulfate. If this was nitric acid, then this would be calcium nitrate. Some methods to lower the effects of acid rain, and this kind of comes into the TOK component of the IB program, how's real-world applications. The switching to alternative or more efficient energy sources, and actually that is a booming industry I mentioned earlier, alternative energy sources, wind, solar. Improving the design of car engines to lower the amount of nitrogen oxides produced. The efficiency of the internal combustion engine is something that's been constantly discussed, and it's a very important issue. Desulfurization, removing sulfur from coal before it's burned. And last, removing sulfur dioxide before it reacts with water by adding it to a mixture of calcium carbonate, calcium oxide, which is called lime, or calcium hydroxide, which is called slaked lime. Slaked lime is just calcium oxide that's been added to water to form calcium hydroxide. Now, all three of these kind of look identical. It's kind of a white powder. Now, each one of these can react with sulfur dioxide to remove it. So calcium carbonate and sulfur dioxide forms calcium sulfate and carbon dioxide. Calcium oxide also reacts with sulfur dioxide. In this case, it forms only calcium sulfite. And calcium hydroxide, slaked lime, forms calcium sulfite and water. So any one or any combination of these three will react with sulfur dioxide to remove the sulfur dioxide, forming the sulfite ion for each one of these. So the key idea here is we are able to remove the sulfur dioxide before it has a chance to react with water to form the acids that we've talked about. Okay, I'm going to show you a review video.
8.5. Acid deposition, sources of oxides of sulfur and nitrogen, and some solutions. Natural sources of sulfur oxides are volcanoes and forest fires. Nitrogen oxides are formed when lightning strikes occur. Now, power stations, if they're carbon-based, release both of the gases, and there are several solutions. We'll see later how those can be reduced or eliminated. You can also replace the power stations with solar power or wind generation, for example. Neither produce those two oxides. A A sulfide smelter, again, there are solutions for that. The production of lead involves smelting sulfide ore. Planes produce nitrogen oxides, as do cars. But you know what? If you take public transport, then that will reduce your emissions by quite a bit. Alrighty, let me land the drone and let's look at again in a bit more detail. So natural sources of sulfur oxides, SO2, SO3, are volcanoes and forest fires. Natural sources of nitrogen oxides, lightning and bacteria. Didn't mention that before. Power stations produce both sorts if it's a carbon-based fuel that's burning. And if you treat that fuel before, during and after combustion, you can reduce the emissions. You can improve design or add a catalytic converter. Don't forget, you can replace the power station with a solar power or wind power, which have no emissions. Sulfide smelter, again, you can treat the chimney exhaust and use an improved design to reduce sulfur oxide emissions. Cars produce nitrogen oxides. They don't produce sulfur oxides. Take the train instead of the car, public transport. And finally, don't forget planes produce nitrogen oxides. And this little bit here, acid polluted lakes can sometimes be successfully treated with calcium hydroxide, otherwise known as lime, which will increase the pH and precipitate out some aluminium compounds.
Okay, that is it. That is the end of Unit 5.